For today's fish, we are delighted to have Albina Mativa from Shell International Exploration and Production. Albina is currently Principal Research Geoscientist and Principal Earth Sciences expert at Shell that she joined 17 years ago after completing her PhD in geophysics and the Center of Wave Phenomena, Colorado School of Mines in 2003. She devoted most of her career to the development of novel technologies for borehole geophysics and low-cost aerial surveillance, and her research contributions have been awarded no less than 3 Best Paper Awards from the SEG. Today, she will talk about distributed acoustic sensing for reservoir surveillance. So please, Albina, the screen bandwidth is yours.
Thank you very much, Adrian, and everybody. It's really my pleasure to be with you today. Okay, here we go. I will give you a little bit of a industry perspective of one of the most exciting applications, I think, in the last decade that has come around in geophysics, distributed acoustic sensing. DAS, as they call it, turns an optical fiber into an array of seismic receivers, and it has many possible applications. I'm only going to discuss one of them, which is DAS VSP, because this is one of the most mature and most versatile applications out there. It's interesting to think that just 10 or 12 years ago, it sounded almost like science fiction. I still remember the very first DAS VSP that was acquired by Shell in 2009. At the time, it was early days. People were looking at the data, squinting at it one way or another, and saying, well, maybe we can get a check shot out of that. And now, these days, you can't go to a big geophysical conference without seeing several sessions on DAS VSP. It's considered technically proven, commercially available, and waiting for business to pick it up. It's really changed the way in which we can acquire and aspire to use borehole seismic data. And the biggest beneficiary of this change has been time-lapse surveillance. That's why the topic of today's presentation is DAS VSP applications to reservoir surveillance. I'll give you a little bit of an overview of where we stand with that. Before I get going, 2 things. Many of my Shell colleagues have contributed to the work that I show you. I can't name them all on this title slide, but you can find their names as co-authors on some of the papers that I mentioned. And the other thing is, I'm obliged to show you this very long and interesting disclaimer, which basically says, please take with a grain of salt any future-oriented statements that I make. Okay, with that, we are free to go. And I assume that most people in the room, in fact, are familiar with the technology, but just to make sure that everybody is on the same page, DAS VSP stands for Vertical Seismic Profiling with Distributed Acoustic Sensing. In a VSP survey, we have seismic sources on the surface and receivers in a borehole. And in the case of DAS, the receivers are fiber. Having fiber in the borehole allows us to obtain 3D and 4D images around the borehole. Let me just check. I'm sorry for interrupting, but you still hear me, right? Something happened a little bit on my side.
Yes, we can hear you. No problem.
Okay, I'm sorry. I'm going back to full Zoom. Okay. So these images that we get from DAS VSP are very, very similar to just normal seismic images, but they have a limited lateral extent around the well, basically some cone around the well. The exact size of that image depends on geometry and the depth of the targets and so on. But generally speaking, imagine an image that is only 1 kilometer or 2 around the borehole as opposed to tens of kilometers as normal surface seismic. Okay, so For time-lapse surveillance, we use fibers that are permanently installed in boreholes, either on tubing or behind casing. But I should mention that it's also possible to acquire DAS VSP using a temporarily deployed fiber. For example, fiber that is incorporated in wire lines that are normally used for just well logging, for example. Those wireline deployments are most suitable for exploration settings or generally wells in which we have some intervention planned anyway. For the purpose of surveillance, we really try to avoid entering the well. So we don't want any well intervention. That's why we use permanent fibers. They make acquisition very safe and easy, non-intrusive, because the only thing that you need to do to get data is to hook up an interrogator to the surface end of the fiber and bring the seismic sources. Having such an easy acquisition is what allows us to do on-demand time-lapse monitoring. And the good thing is that we can install a permanent fiber in almost any type of well. It can be injectors, producers, and they can be active during the VSP survey. We don't need to shut in the wells in order to get VSP data. That's impossible with geophones, for example. And of course, the same fiber can be used for many other applications, such as temperature sensing, DAS for flow, and so on, which enhances the value of the fiber installation. Maybe the most important thing to realize about the use of fiber is that it's not simply a poor man's geophone, but instead, the way we look at it is as an enabler of novel borehole seismic applications that were previously impossible with geophones, either for technical or for logistical and cost reasons. Okay, so I already mentioned that the biggest beneficiary of DAS is reservoir surveillance. That's why I'll spend most of this talk talking about 4D applications, onshore and offshore, but with an emphasis on offshore, and especially deep water, because that is where the biggest impact is. However, before we get to 4D novelties, I would like to revisit some classical 3D VSP applications, because a DAS VSP is still a VSP, and if you would be getting 4D data, you're anyway getting 3D data too, so you may want to know what to use it for. You will notice that my slant here is very much about why we use or don't use certain applications, and not so much on how we actually do it. I know that you care about how. I will say a few words about that toward the end, but then please feel free to ask me anything that I didn't mention during the talk. Okay, so starting from 3D, a textbook case for using a VSP is for imaging under complex overburden, such as, for example, salt. For subsalt imaging, it's known that 3D VSPs can provide an uplift to image quality, but it used to be expensive, very expensive, to do 3D VSPs with long geophone strings as required for subsalt imaging. So this is one example in which DAS basically enables us to do something that has long been wanted, but just it was cost prohibitive in most cases. In this example here, let me turn on my pointer. Okay, this example here for subsalt imaging is from a well, a producer, very active producer that was drilled through salt. So you can see that the image that you get from the DAS VSP is not very extensive laterally. However, we get to see exactly where we care to see, which is where the well penetrates the subsalt sediment, and the image is an obvious uplift compared to surface seismic in that area. Another type of complex overburden is the near surface onshore. It's notorious for causing problems with surface seismic 3D, but it's even worse for 4D. So in this case, VSP helps in several ways. One way is that reflections pass through the complex overburden, complex near surface only once instead of twice. The other is that the receivers are below the surface, and therefore they hear less surface noises, most notably less ground roll, which is very difficult to clean up from 4D data. And perhaps the most important part is that any change and complication that happens near the source, whether due to the near surface or the source itself, can be measured using the direct downgoing arrivals from the source to the downhole receivers, and then used to correct the reflections for that change. So that's why DAS VSP is also beneficial to onshore surveillance. Okay, another iconic 3D application of VSP data is using the first arrivals for travel time information. So in the case of DAS, the notable thing is that you very easily get large surveys like 3D and 2D as opposed to just one shot next to the well. And that allows you to do some pretty good travel time inversions, such as for anisotropy in sediments. It also allows you to create virtual source data. You might remember that 10, 15 years ago, virtual source was a very hot topic in the VSP community, but it requires as input at least a walk-away VSP. And with geophones, that was a stumbling block because it was expensive to get anything beyond the 1G VSP. So essentially, here again, that's a case in which the simplicity and lower cost of DAS enable us to get the necessary input data to do that. It's useful for seeing under complex overburden. It's also used for getting very accurate interval velocities. Another thing is, if you have a well that is near salt, whether it is just outside salt or just inside salt, you can use the data for salt proximity or sediment proximity type of applications, which aim to tell you where the salt flank is. The benefit with DAS here is that you have a very long receiver array, which allows you to move from array-based applications, array-based salt proximity type of surveys to using full waveforms to image the salt flank. For example, RTM is a pretty good tool because it can handle multipathing that can occur quite easily if you have a very rough salt topography. Okay, so bottom line is DAS VSP, even though it's mainly used for 4D, it can also help the various classical 3D applications simply by making the data available. Okay, so now going to time-lapse. Time-lapse, let's first look at onshore. Onshore, there are several domains of application. The very first idea that we had when we became able to record 3D VSPs was that we can use them in fields that are undergoing enhanced oil recovery. Some of those fields, especially in the Middle East, tend to be drilled on very dense well patterns. So we thought, okay, we can install a number of fibers in a bunch of wells and have them all listen simultaneously to the same carpet of shots and get a time-lapse surveillance through repeated 3D VSPs that overcome all of those challenges with the near surface that I mentioned 2 slides ago. However, when we tried that, we very quickly found a problem. The problem was that these EOR fields have a very congested and fast evolving infrastructure, which obstructs source access. You get big gaps in the source grid, and those gaps are not very well repeatable. They harm both 3D images and 4D images. So this application is currently on hold because of the surface obstructions. Another domain of application is unconventionals. That's really the birthplace of the DAS technology, and there is an amazing variety of fiber optic applications in unconventionals. The VSP is only a very small portion of that, but it allows you to see some very interesting things. You can do repeated VSPs between frac stages to monitor the dynamic behavior of the induced fractures, their opening and closing and their geometry and so on. So it sounds all very attractive, but what is the missing link here is more integration with other fiber optic applications so that these observations of the fractures actually lead to actions in the field. Without such actions, businesses simply will not deploy a certain technology. So in the case of unconventionals, this is partially a technical, but partially also stakeholder management issue. And maybe, okay, one last domain of application, arguably growing, is CO2 sequestration. So you know that humanity has the ambition to store more CO2 in the ground. And in doing that, it's critical to be able to monitor the safe storage of CO2. So it's mandatory, it's related to the license to operate, to have some monitoring and verification plan. So DAS VSP, because it has better repeatability than other tools onshore, is actually an excellent candidate. You can put your fiber in injection wells and then, even without stopping the CO2 injection, monitor what's going on around them, both for the purpose of conformance, which means knowing how your plume is evolving, as well as containment, which means making sure that the CO2 stays in the intended reservoir. We have such example, one of the very first commercial deployments of CO2 sequestration. We had it at Quest, which is onshore Canada. Since 2015, they have injected more than 5 million tons of CO2, and they do that through 3 injection wells. Each of those has fiber behind casing, and each of those has multiple vintages of multi-azimuth walk-away VSPs acquired. As I mentioned, those are used to verify conformance and containment. It's quite easy to observe the evolution of the plume over time. A recent reprocessing of this data set, in fact, led to a repeatability level of what we call normalized RMS, that's a measure of noise, and RMS, below 10%, which is truly excellent for onshore. Okay, so one of the challenges here is that sooner or later, these CO2 plumes will outgrow the area of illumination from DAS VSP, and then the question will be what to do next. That would depend partially on what the need for monitoring at that point in time is, which in turn depends on how predictive we have proven our reservoir models to be. So one of the things that needs to be done with DAS VSP data at the early stages of injection monitoring, other than simply looking at the plume evolving, is using the data to calibrate the reservoir models so that they have a better predictive power, so that in the future, less monitoring is required. So that is for onshore. For offshore, the story is a little different. There is one main domain of application, which is for frequent monitoring in fields that are undergoing some complex type of recovery, such as either water injection or some other type of stimulation, injecting something. So normally, these fields are being monitored with OBN. That's the gold standard for time-lapse monitoring in deep water. OBN is a type of survey that uses nodes, seismic nodes on the seafloor. It gives fantastic data over large areas, but the problem is that it's very expensive. So you cannot afford to do it very often. If you do a survey that is only several years apart, that is good for making decisions that have a long lead time, such as, for example, where to drill the next well. But it's not enough for making decisions that have a much shorter time scale, such as optimizing operations in existing injectors and producers. So that is where new technologies such as DAS come in. Being lower cost, they can show you what's happening in a certain small area that is of interest at this particular moment. And you can imagine that if you can see just what you need to see at any given moment, that may also allow you to postpone a little bit the wider, more expensive surveys. So in the long run, having some flexibility with OBN scheduling is a cost-saving strategy. However, doing such frequent monitoring is actually not easy because there is a set of non-trivial requirements for the monitoring tool. It must be low cost in order to be able to afford frequent acquisition. It must be available on demand to answer urgent questions. It must be non-intrusive to not deter use. And at the same time, it must be sensitive enough to detect the small changes that will happen over a small time interval. So you can see that some of these requirements are contradictory. For example, low cost and sensitivity. For that reason, the entire evolution of DAS VSP in deep water has been very much centered on striking the right balance between sensitivity and cost, or maybe to put it in another way, do the lowest cost acquisition that would still give you enough sensitivity to see something, what you want to see, with enough confidence. So I will not bore you with all the details of maturation steps in deep water, but I can tell you that it took a lot of field testing of everything that you could possibly imagine, from the logistics of acquisition to the well conditions, flowing, not flowing, where the fiber is, what type of fiber, what type of geometry. Then it also took lots of efforts to reduce the source effort to the minimum amount possible by shooting sparser shot lines, by using smaller sources that can be handled by lower cost vessels. Basically, we do everything possible to harm our data quality, but amazingly, DAS VSP keeps performing and we are able to get fairly robust time-lapse performance. We get this measure of 4D VSP repeatability below 10% very routinely, even under horrible well conditions in deep water. So we have tested this performance in two ways. One is that it's just in terms of time-lapse noise. The other way is by comparing the results from DAS VSP to OBN 4D, which means we have eavesdropped to various OBN surveys. However, I want to point out the obvious, that the only time you get new information from DSP is if you use it between OBN stages, not during OBN stages. Anyway, let me maybe just jump and show you some examples of what type of information you can get from that. Here's one example. It's about monitoring the startup of a new injector. So we had a DAS VSP between two OBN surveys that happened to capture the startup of a new horizontal injector, which has been online for less than 6 months. You could see the hardening signal, this blue blob related to injection very clearly, but it was only at the toe of the well. This is not what was expected from the reservoir model. It expected something else, and it prompted investigations as to what is the root cause. Is it the completion? Is it the reservoir model? Eventually, we found out that it's probably the reservoir model because we had a resistivity log that was showing more residual oil saturation before this injector was drilled. This is a log in this injector before injection started. So it had more oil toward the heel and more water toward the toe, which was exactly the opposite of what our starting water saturation model was. According to the model, we were expected to have more water toward the heel and more unswept oil toward the toe. Okay, so log plus DAS led us to update the reservoir model to honor this more complex permeability pattern. If we didn't get this DAS VSP in 2017, and if we had waited for the next OBN, which was just 1 year later, it would have been a lot harder to spot this type of behavior, even though it was still there. It was just harder to see. So then the next question is, does it matter, and what the water does next? Specifically, reservoir engineers wanted to know whether the waterfront might be headed preferentially toward one producer or another. So, okay, we got some DAS in 2019, and to the surprise of everybody, we found out that the hardening signal corresponding to injection had barely expanded. So basically, that told us there is little progress of the observable waterfront. Emphasis on observable, because that doesn't mean that water is not moving. It just means that perhaps it's moving away from this injector along some thin layer, the net thickness of which is not enough to be visible on 4D DAS VSP data, especially when the visibility of it is offset by a certain level of softening that can be related to pressure up, for which we see some indication in this data. So blue generally means in our plots hardening, while red means softening. So we can see that this blue blob is less blue than that blue blob, which can happen when you have some red on top of the blue. Okay, that sort of explanation. Anyway, so this points to the fact that this is a very complex reservoir that needs further monitoring, because the current hypothesis is that injection is happening in a sand body with a limited connectivity. This type of information is really of interest to assets that operate these fields, because if their sweep is not performing as intended, they need to know that and do certain things to help improve the sweep. Another type of application. Now, this is in a different reservoir in which injection is older. By the way, this reservoir is in the same field as the other one, just at a different depth. So it's being monitored by the same DAS surveys. We had that survey in 2017 that basically showed that water is progressing directly up dip. These are depth contours, so up dip from its previously known location. And it seemed to be following a certain preferential path that looked nothing like the C-shaped uniform reservoir model that we had at the time. So once again, opportunity to calibrate our reservoir model. Then, when an OBN came the following year, we noticed that the water propagation had changed direction. Instead of continuing going up dip, it was now headed directly toward the nearest producer. And this change of direction was also confirmed by a DAS observation in another well. This led us to predict that water will arrive at this producer by a certain quarter of a certain year. So the interesting thing about that is that this is a very tight prediction. Typical reservoir models have an uncertainty of about a year as to when the water will show up at the producer. But what production technologists want is a prediction that is better than 6 months uncertainty. This is their magical number that allows them to plan certain well treatments, as well as logistical things like the frequency of fluid sampling. So in this case, we had this ambitious prediction, and it came true. Right at the end of February and beginning of March, the water content in this well shot up. Armed with confidence based on that, the next thing that we wanted to see was what the water sweep would do after it arrived in this producer, because there are several other producers in this field. 2 of them are in the attic over here, and one is to the south, and with a suspected baffle between it and the nearest injector. So we got another data set with DAS in 2019, and we saw very clearly how the baffle is indeed there, and the sweep is progressing up dip toward the attic producers, but not toward this producer to the south, which helped the asset basically prioritize wells for scale treatment. That's a type of treatment that they do before water gets there. That doesn't mean surprises don't happen though. A little later, some water did arrive into this producer sooner than we expected. So now the question is why? Is it that this baffle was in fact leaking all along the way, along some thin layer that is basically at the noise floor of our 4D data? Or is it that soon after we acquired this survey, water found its way around the baffle and on the highway to this producer? So that is what we hope to find out with the next survey. So I would say, I hope I show you these examples to from which you hope you gather that we can see various quite useful and interesting things in our data. And you might say, okay, we are in great shape. Why isn't industry using this technology all over the place? It's not so simple, because in order to deploy this thing, what you need for a particular field is something like this. If I see a certain time-lapse signal, I'm going to do this and that. And the business impact from that would be ABC. And okay, it's easier said than done. This part here about expected observed signals. Geophysicists are excellent at doing predictions of what kind of things can be and can't be seen. But what can be done, that is in fact the specialty of other disciplines, the disciplines that in fact operate the wells, which are reservoir engineers and production technologists. It's not the geophysicists. So here, cross-discipline collaboration is absolutely essential. Disciplines must speak each other's language and understand each other's options and problems as well. So, okay, people are working on that, but just that's one reason why it's not so simple to deploy things. Okay, with that I will stop about the organizational type of challenges and say a few words about how we actually do things. Well, currently we do things in the simplest way possible. So for example, for imaging, we currently use primary reflections. And in order to make the image wider, what we normally do is record DAS VSP data in several wells at the same time, listening to the same patch of shots, and then we combine these images from the various wells. There is another way to do this though, which is based on using multiples. The benefit of using multiples over primaries is not only that you can get a wider image from one well, but also that you get a nice image above the VSP receivers, where normally you wouldn't see with primary reflections. So in 3D, imaging with multiples in various kinds and flavors of how to do it has been around for many, many years. However, what is still not mature is the maturation in 4D. You have to make these multiples contributions more repeatable. Another thing that people often ask about is the pre-processing before imaging. So if you look at the processing workflow, you will notice that, in fact, it's a combination of some very typical VSP processing steps and some very typical 4D processing steps. The only thing that is DAS specific is one step which is related to depth calibration. So what is the issue here? The issue is that when you use DAS, you know your receiver positions along the fiber, but the fiber position with respect to the rock formation is uncertain, and that's related to complications with the fiber installation in the wells. So in industry, there are various depth calibration methods out there. One of the methods that Shell favors is a method that utilizes amplitude information, DAS amplitude information. So, okay, think about Hooke's law. DAS essentially measures strain. If the receiver is next to a soft rock and you impinge with a certain pressure wave, it will deform a lot. It will deform much less if the rock is stiff. So basically, that is the mechanism through which DAS amplitudes depend on the local formation properties. This can be used in two ways. First of all, in 3D, in order to find out the absolute position of your fiber with respect to the rock formation, you can correlate DAS amplitudes to available well logs. So DAS amplitudes are a routine, like, okay, DAS scalars, as they call logs, and you try to correlate the DAS scalars to the well logs. Right now, in the DAS community, there is quite a lot of debate. What is the exact combination between density and sonic logs that is proper to correlate DAS amplitudes to? This question can be quite important if one's ambition was to use DAS amplitudes in order to invert for local properties of the formation, such as stiffness. However, for the purposes of depth calibration, I don't want to say we don't care, but we can be a lot more relaxed. There are many combinations of logs that visually can very clearly tell you where your DAS is with respect to the Earth formation. So for depth calibration, you can get away with more qualitative things. We typically use something like Rossi squared to correlate things. Then another thing is that in time-lapse sense, you don't even need the well logs. What you can do is you get these amplitudes of DAS extracted from each vintage of the VSP, and then you cross-correlate them between themselves. That's much easier because you have DAS all over the well, unlike logs, which are only present over a short interval of the well usually. So basically, it's much easier to correlate DAS scalars to the wells, not to mention that you're correlating the same type of data between vintages. Anyway, we can talk a lot more about this, but I don't want to spend disproportionate amount of time on that. Let me say a few more words about outstanding challenges and needs in skills. So notice how here we have classical VSP processing combined with classical 4D processing. There is no magic, but you may be surprised to realize how few people actually have this combination of skills. Many people have one or the other, but not both. So when it comes down to processing, DAS processing, success hinges on having the right combination of skills. That is also true for other things. So the right combination of technical competencies can help you get the most out of DAS VSP data. For example, knowing how to use seismic and in-well DAS surveillance, for example, for production profiling or injection profiling. I already emphasized multidisciplinary engagement. It's never too early to start learning the language of other disciplines because geophysicists cannot work in isolation. And last but not least, stakeholder management. People think usually that technologies kind of would popularize themselves if they're sufficiently good. Nothing is further from the truth. It's all about being able to balance the needs, requirements, and viewpoints of different stakeholders in the given field. So that is also a skill very worth developing. It's a learned skill. And again, never too early to start. Okay, so a little more technical things. There are some things that have been a problem in VSP processing for many, many years, and somehow it has never been fully addressed. One of those things is I told you that we like the opportunity to use direct wave, direct arrivals, so basically downgoing arrivals measurements to see what's happening in the near surface and then correct the reflections for overburden effects. Those overburden effects can include shallow multiples. The issue is that with far offset VSPs, basically, the path of the downgoing and upgoing arrivals to the DAS receivers are not similar anymore. In the classical VSP applications, you have a 1D situation. The source is next to a vertical well. So then you quite literally deconvolve the upgoing wave field with the downgoing wave field, and you suppress all of this overburdened complexity. Not so at large offsets. There's some methods for dealing with the difference between downgoing and upgoing waves at large offsets, but those rely on lateral invariance, so basically horizontally layered medium. What if you have a more complex medium? There is no analytical solution to that. There is no general solution to that. So these days, one of the ideas is that it may be worthwhile to try machine learning, basically to learn how you can predict, how you can clean up the reflections from these shallow complications when you have both the downgoing and upgoing. Okay, another thing. DAS is not a geophone, so in many ways. And instead of fighting that, we'd better use it. One of the things is that we record DAS VSP data in active wells. That means a tremendous amount of noise, but instead of simply throwing it away, we can try using it. A typical example of that is using tube waves for completion monitoring. So that's something that is going on at various levels at different projects. Another thing is, okay, DAS is not a point sensor. What DAS really measures is the stretch or squeezing of a certain length of fiber called gauge length. And so it's a linear sensor that is along the borehole. One of the choices that people make in acquisition is to set what gauge length you want your data to be at. And that is related to the signal to noise ratio as well as the resolution of the output data set. But the typical direction of thought on that has been, well, let's optimize the gauge length for different wavelengths, for formations with different velocities. You may want a different gauge length. Then let's choose the best gauge length. What about, instead of choosing the best gauge length, you may want to try to combine different gauge lengths in order to exploit them somehow in order to get higher resolution, spatial high resolution data. So, okay, I'm just mentioning these things in case you have some energy to deal with any of them that could be of potential interest. And then one last thing that is totally within industry domain, not so much academia, but it's about maturing DAS systems for subsea wells. Everything that I showed you so far was for wells that have a dry tree. So basically, you have a platform offshore to which the fiber goes. But there's subsea wells in which the wellhead is at the seafloor. And in those wells, for now, there are very few fiber installations. They're starting to come, but it's slow because the hardware is there with some limitations about the conditions. So eventually it will come, but when it comes, the applicable base would be much larger. One thing to know about this is that it's not just about hardware, it's also about the interrogation system, because in these subsea wells, you would have many connections between different pieces of fiber. And when you have these connections, each of them has a big optical loss, and fibers tend to be longer as well, which is an additional optical loss. So basically, normal DAS interrogation systems that are suitable for short wells onshore are not going to be suitable for subsea, and vendors are working to address that. With that, let me sum it up so that we have a few minutes for questions. So really, DAS enables both classical and novel VSP applications, mainly through allowing non-intrusive low-cost acquisition. And it's a true step change in our ability to monitor rapid and localized subsurface changes. The technical capability of 4D DAS VSP have been proven very well by now by multiple field trials. Onshore, maybe the most important application is for CCS monitoring because we benefit to other seismic methods. Offshore, the biggest trend is complementary to OBN. And there are definitely further opportunities to leverage this technology. And with that, thank you very much. And I'm happy to answer questions.